All right, welcome everyone. Very happy to be here with you all and share some insights that I have on searching and sorting techniques. So we'll be going over searching and sorting algorithms today. And if you have any question at any moment, please feel free to stop me and ask the questions. So first, we'll be discussing over binary search. This is one of the commonly used algorithm. So let's get started. Okay, so in case of linear search, if you want to search an element in an array, what you normally do is go over every element one by one, and until you find that element that is a target. So in that case, it's doable, but then the complexity is O of n, where n is the size of the input. So what that means is, like, if there is an array of size 100 and you want to search an element, assuming that the element that you have is in the 100th position, you end up like going over every single element, visiting every single element in the array. So this is definitely doable, but then there is a more efficient algorithm way to do it, and that's when binary search comes into picture. So in binary search, the time complexity is reduced from O of n to logarithmic n. We'll see how that happens. But in order to understand binary search, let's take this example. Let's say you have a word with you, and then you want to search the meaning of that word in the dictionary. I see Jing has raised the hand. Did you have a question, Jing? Or
I think maybe you want to start a slideshow.
Okay, so you have, you're not able to see my screen, the binary search screen, or?
Yeah, I think what we can see is the overview. So it's like showing next slide and your slide order.
Okay.
I think you just might have to switch to a different screen.
Okay, sure.
We can start recording.
Is it better now?
Oh yeah.
Yes.
No. Now we can see it. Perfect.
Okay, sure.
Thank you, Maha.
No worries. So, okay, going back. So let's go back to our topic. So if you want to search a word in a dictionary, there is one way to do it, where you can start from the first page and search word by word. If it's sorted in the alphabetical order, you can go one by one and see where your alphabet lies, and then find the meaning of that word. There is more efficient way to do it. I'm not sure if anyone have tried that. If you have a word and you want to search in the dictionary, what are the common ways would you do? Like, rather than going from alphabet A to B and turning over pages, flipping on pages, does anyone want to unmute and tell, or share it in the chat? Okay, so maybe like one of the way that we can do it is like open in the middle of the dictionary and see what word that you have, what alphabet that you have there, compare with what you have, the word that you have, and then kind of decide where to navigate, either in the right half of the dictionary or in the left half of the dictionary. Let's say you want to search for a letter T, and then you end up in the middle, M. So now you know that you don't have to go in the left half of the dictionary. All you have to do is go from M to the end of the dictionary. And when you search in that portion, you'll be able to find the word that you have. So binary search works on the similar concept, where so one condition that you need to have for binary search is it works only on sorted arrays. So the array has to be sorted. And then let's see in detail how that happens. So here you have you find a middle element, and then compare that middle element with the target element you have, and kind of decide where to search in the array. either in the right half of the array or the left half of the array. Okay. So here there is an array that starts at number 11 and ends at number 17. It's sorted in ascending order. And now you have 2 pointers. We take 2 pointers, start and the end, and find the middle element of the array. The next step is to compare that element with the target element that we are supposed to search for. In this case, the middle element is 14 and the target element that we want to search is 12. Now, once you compare, there are 3 possible outcomes. The middle element could actually be the target element itself. In that case, you return that middle element right away. The other 2 cases are the middle element is greater than the target element, or the middle element is lesser than the target element. So in this first case, the middle element is greater than the target element. So now we know for very sure that our target is going to be in the left half of the array. So what we do is like we move the end pointer from here, we move to the mid index. You bring the end pointer to here, and all we need to do is keep repeating that, finding the middle and kind of navigating whether to go left or right from start to the mid index. So that's as simple it can be for the binary search. Let's say, let's take this example where you have a middle element, and now you compare that with the target, and here we can see the mid element is lesser than the target. So our target is going to be after mid for sure, towards the end of the array. So we can narrow our search window from the mid to the end. So we keep doing that until the start pointer until the start and the end converge. So the condition will be like start is less than end. So you keep doing that, and you will end up in one of the 3 conditions. Your mid could actually be equal to the target itself. In that case, you'll return the mid as the index of the target element. Otherwise, you keep switching the start and end pointers until you find the target element. So, so here is the binary search algorithm. It takes an array, and then you have the mid index, which is calculated by using this formula: start plus end minus start by 2. You can certainly do start plus end by 2, but I prefer to do start plus n minus 2. The reason why is because it prevents integer overflow. Let's say like you're having very large integers, you don't want to sum up both and end it. You might end in integer overflow, whereas if you use this algorithm, it's more safe. I mean, this formula, it's more safe. So once you have the mid, then the next thing is to compare the mid with your target item. This is supposed to be item, which is the target element that you're searching for. It's not size. I think it's a typo. So pardon me for that. And once your item is, which is your target, that is, if it's the middle index, you're returning the mid index. If not, you keep changing your start and end pointers, whether to mid and so here we have to decide whether we have to change the start or the end based upon the values. If that item is greater than mid index, then you move your start pointer. Otherwise, you move the end pointer to the mid index. So the best time complexity is O of 1. Let's say you have the middle element, and the middle element itself is the target. In that case, you found your target immediately. So the complexity would be O of 1. But in other cases, it's a logarithmic of n, because let's say you're adding twice the amount of elements in your array. In that case, every time you're cutting the array into half, you're skipping the half of the elements. So it would get reduced to logarithmic of n, whereas in linear search, it is O of n. Jing, I see your hand is raised. Did you have a question?
Oh, I don't. I think, I should,
Okay.
I just cancel. Yeah.
Okay, no problem. Someone else? I couldn't see their name. Hey.
Hi. You mentioned an idea to shorten it. I'm not sure which line where you said you would prevent an extra condition by evaluating it first.
I'm not sure I understood your question. Can you please repeat it for me?
Sure, I'll listen closely to how you explain it next time. You eliminated a condition by checking something first, and here we're checking if it is equal. But I'm going to ask again when we discuss it, since there and point to the line then.
I think it was a start plus n minus start by 2 condition where you explained why you are doing so, right? Maybe that was it.
That sounds right, to decide if you're going to the left or right. I don't know who said that, but yes, that sounds right.
Yeah, maybe you can explain that again, please. I mean,
Okay,
the question is why we are not using star plus n by 2, but using star plus n minus start by 2.
Oh, okay. Here, so that's what I said. Like, let's say your start and end are like very high. The numbers are huge. So integer has a certain capacity of elements that it can hold. So when you do start plus end, it can already exceed the integer limit. In that case, you'll be having an integer overflow error. Whereas here, what you're doing is, let's say it's both start and end are very large integers. So you're having start, you're adding, with start, you're adding n minus start by 2. So that will reduce the actual value of it, which will prevent it from integer overflow. That's why it's a more preferred way of calculating mid rather than using start plus n by 2. Did that answer your question?
That was the question. I'll take a look at that, because here, when I don't see start divided by 2, even though here you have the end divided by 2.
So we're not doing start divided by 2. We're having start plus end minus start by 2 here.
Okay, thank you.
Was that helpful, or let me know? Otherwise, we can certainly talk about it if we're not. Okay. Cool.
So when we say start, we are calculating the index, right?
Yes, we are initializing 2 pointers, which is like start will be. We don't have it here, but let me go back to the previous slide.
Because I'm just curious, an array starts with an index of 0.
Yeah.
So if we say end minus start, which means for an array of like 10 elements, it would be 9 minus 0 divided by 2, right?
Mm-hmm. Yeah. So let's take the example here. We'll go over this element. Okay, so we have 0 and 6. Let's do that here. Your start will be 0. Plus 6 minus 0 is 6 by 2 is 3. So your mid index would be 3, which is just this element. What was your example?
I think I'm good. I'll just look at the index overflow scenario to understand that formula better. Thank you.
Okay. Let's keep moving forward. So, there are three possible outcomes. The one is equal to and greater or less than. So this is the common algorithm used for binary search, but there are some variations in binary search as well, like where it's not a straightforward binary search, but some tweaks. So you may want to look at finding like a rotated array and finding an element in a rotated array. So those are variations of binary search. Other than that, moving forward to our next slide. This is another example of binary search. It's just similar to what we discussed. I don't think we have to go over this. It's calculating the mid, comparing it whether it lies in the right half or left half. If anyone didn't understand how binary search works, please feel free to unmute or give in the chat. We'll give the explanation again, but otherwise, if not, we'll get to the next topic, which is our sorting algorithms. We'll start with insertion sort first. All right. So in insertion sort, sorting, what happens is we are going to order the elements, actually sorted. And how we are going to order that is having a small subset of the list. Like have this, consider this first element as a sorted, is already sorted. So here, let's assume that 7 is already started. And starting from the next element, compare that with the previous element and see if it's smaller or greater. If it's smaller, then it has to come before this element. So in that case, we do a swap. So here we swap 7 with 6, and then keep moving forward and compare with the other elements in the array. And let's take the element 10 here. So when you compare 10 with 7 and 6, it's greater than 7 and 6, so there's no swap needed. And then you move on to the next element. So here, 8, then 8 is compared with, I think it's better if I have a pointer. Just a second. So the next element is 8. 8 is compared with 10. So 8 is lesser than 10. So we need to swap 10 with 8. And we have done that here. And then comes 11. 11 is compared with 10. It's smaller. Compared with 8, it's smaller. It's compared with 7, 6. So you keep comparing the elements prior to it to make sure that it is those elements are smaller. If it is greater, then you perform the swap. So you keep shifting the elements as needed. Okay. So how that sorting happens is the lowest element will go in the left and the highest element will go in the right. The complexity of this is O of n square, and the best case scenario is O of n. We'll discuss how that works. But first, let's go over an example. An element. Okay, cool. Here's the code for insertion sort. So what we have here is a method, insertion sort, that takes an array, and n is the length of the array. We are iterating over the elements from the start to the end of the array, having a temporary variable that holds the element that we are currently visiting. And we have another pointer j that starts with I, and it keeps checking the elements, like the previous elements, its immediate previous element, to see if it's smaller. In case if it's smaller, we are just shifting the position of that element and decrementing j counter to compare the next previous element. So we'll see how this is being done. And once you compare and you find the correct position of that particular element, then you place that element in that particular index. Let's understand this with an example. Here we have the list that has elements 4, 1, 3, 2, 5. Starting with, you assume that the first element is already sorted. So we start with the second element in the list and compare the second element with the first element. So here I is 1 and temp will hold whatever value I has. So the element at index I, which is 1, temp will hold 1. And j is initialized to whatever I is. So first time j will be 1. So here j is equal to 1. If j minus 1 is greater than temp, here is j minus 1 greater than temp? Yes, the 4 is greater than 1. So what you do is you copy that 4, you copy that 4 to the right, and eventually 1 should come here. So we place 1 over here. Now the array becomes 1, 4, 3, 2, 5. Now increment the index counter from 1 to 2, and temp will hold the element at index 2, which is 3, and j will be initialized to i's value, which is 2. So in this case, we are comparing 3 with 4. So 3 is smaller than 4. So 4 has to be moved right. So you're placing 4 into this index, which is this line of code here. A of j will hold a of j minus 1. So 4 is copied to this element. Before moving 3, we check if there are any other elements in the list that has to be sorted. So j's counter will get reduced from 2 to 1. And in this case, 1 is already less than 3. So we are good. We don't need to check again, but we will exit out of this while loop. And then we'll place this element 3 in index here in index 1. J's value will be 1 finally. So it will place at the first index, which is the index 1, which here will hold 3. And now the counter will get increased from index 2 to index 3. And element at index 3 is 2, temp will hold 2. And j will hold whatever, j will start with where I starts. And first, initially, j's value will be 3. We are comparing 2 with 4. 2 is lesser than 4. So we know that 4 has to be shifted towards the right. We are not placing 2 into this index yet because we have to check if there are any other elements that are smaller than 2 in our list. So we decrement j's counter from 3 to 2, and we compare if 3 if it's lesser than 2. So 2 is lesser than 3. So 3 also has to be moved towards its right, to the right. So 3 will be copied here. And now j's count will be moved from 2 to 1. And then you compare 1 with 2, 1 is less than 2. There are no more elements to compare. So you finally place this 2 at this index, at whatever value j is, and j would have the value 1. So you place the element here. So the array now becomes 1, 2, 3, 4, 5. We are not done yet because we have one more element, 5, to check. I is 4, temp is 5, and j's value will be 4. You compare the element previous to it. 4 is less than 5, which is good. So it's not going to go inside this while loop at all. It will, and there's no swap needed as well. So yeah, that's how this insertion sort works. Before moving to the insertion sort, let's see why this is O of n square. So you're going to visit every single element in the array. Like you have to check every single element in an array. But for checking every element, you're also checking the elements previous to it. You're comparing the elements. You have this another while loop that keeps checking another element in the array. So that's why in the worst case, it becomes O of n squared. Best case is O of n, because here, let's say this is our best case where the array is already sorted. So in that case, we won't hit this while loop at all. You just keep checking the elements, and it will be lesser. Temp will always be lesser than the j minus 1, so you don't have this. It will not hit this while loop. So in that case, it's O of n. Cool. Now let's go on to our next sort, which is selection sort. Okay, selection sort is an in-place sorting algorithm as well. How this works is you're going to find a smallest element in the array and swap it with the leftmost unsorted element. So, and keep doing that again for every element in the array. Let's see how that works. So here is an array that has 7, 6, 10, 8, 11. We have an index counter at the first element, like our index count, or let's say, to make it simpler, let's say count variable. So count variable is 0. And now starting from 1 till the end of the array, you're going to find if there are, what is the smallest element. So here, the smallest element here is 6. Once you find that smallest element, we are going to swap that with our, the element at index 0, or the element at our counter variable. So, and then once you perform that swap, increment the counter variable from 0 to 1. Now starting at index 1 till the end of the array, find the smallest again, and whichever is the small. Once you find the smallest element, you swap that element with index 1. So now here we have 6, which is already the smallest element. So there is no swap needed. Now incrementing the counter from 1 to 2, see which element is smaller starting from this index. And then you have 8, which is the smallest element. Now you swap that smallest element at index 2. Now increment the counter to 2 to 3, and then keep doing that until the end of the array. So here you have 10 and 11, which is already the correct. I just want to run this with an example. So if there are anyone who want to understand it better, it will be useful. So let's quickly go over this before we go into our next sorting algorithm. 9, 4, 3, 1, 10. We have to sort this in ascending order. So we have to look at one element at each, every time. So now we know that the whole array, 1 is the smallest. So we swap it at index 0, or it's already in the correct position. So we don't need to swap. Now increment the index count from 0 to 1. And starting at index 1, what is the smallest element? It's 3. So now we swap 3 with index 1. So the array becomes 1, 3, 4, 9, 10. Now increment the index count and see what are the elements that is smallest starting from index 2. 4 is already at the right position. There are no smaller elements after that. So 4 is at the right position. Now we increment the index count and we loop through to see if there are any other smaller elements less than what is the smallest element. There are 9 is no, 9 is the smallest. It's at the right position. So no swap here. And now you increment the index count to 10, and 10 is the last element and it's the smallest. There are no elements after it. So there is no swap. The sorting is complete. The array is sorted from 9, 4, 3, 1, 10 to 1, 3, 4, 9, 10. So here the complexity, it's going to be in the best case, or in the worst case, it's going to be O of n square, because you end up finding the smallest element for every element in the list. So basically you're going over the array, like going over the array for every item, which leaves us with a complexity of O of n squared. Awesome. So that's about the selection sort. Any questions, thoughts? Here's a code for selection sort. So you have the selection sort method that takes an array as an input, and yeah, I see questions. You can type it in the chat, or you can unmute and okay. So here you have the length of the array in the variable n, and you go over every element, and for every index you have to find the smallest index, the index of the smallest element. So in that case, you have another for loop to go over the entire elements in an array starting at index I plus 1. And if we see if there is an element that's lesser than the element, the A of min, then we initialize that, we consider that index as the minimum index. So the element at that index is holding the minimum value. So we have the min index. And finally, once you find the index of the minimum element, if I is not equal to min, so this condition is added so that you don't end up swapping if it's already in the right position. If not, then this is a normal swapping method. You have a temp, and temp will hold A of I, then you swap I and A of min, and finally A of min will have temp. So this is the swap portion of the code. Let's go over the next sorting technique, which is the merge sort. Merge sort is commonly used sort, and in merge sort it has two steps. One is the splitting portion of it, and second one is the actual merge portion of it. So if there is a list of elements given to us, splitting the elements into left and and have them in left and right array. Keep doing that until you have an element, just one element left in the list. And then once you have the the array like with only one element, now you merging, and once you before you add it to the result array, we kind of sort it again. This is being split into the left and right. Here, this array is again split into left and right. This has been done repeatedly until you end up having only one element in the array. So now the split step is complete. The second step is the merge step, where you compare the left and the right and see if it is smaller. You perform the necessary swap and then sort it and then add it to the result array. So here there is 86 and 57. You compare it, sort it, and add it in a sorted way, 57 and 86. We'll see in detail how we are doing that, the merge step. But this is just an overall, just to give you an overall idea how this algorithm works in general. We'll get into the nuances in the next slide or so. So, so you have the left and the right. Comparing that again, consider this left and right. Now you sort these and then add it to the array. So until you get only one list, after these kind of sorting, after you keep repeating the steps until you find you end up with only one list. So here is a code for merge sort. So here we have a method that that takes an array, and if the length of the array is greater than or equal to 2, only if there are 2 elements left in the array, we can divide them into left or right half. If there is only 1 element left, then it means it's already split. So if the length is greater than or equal to 2, then we have 2 arrays, left and right. This left array is what this left array will hold is from in the original array, from starting at index 0 to length by 2. What that means is the first half of the array. So starting from index 0 to that index, you keep adding elements from that original array to the left array. Let's say we have 1, 3, 2, and 4. Okay. So our left array will hold elements 1 and 3, and the right array, starting from the mid to the end, it will hold elements 2 and 4. So this is this, and then you call the same function merge sort with the left array and that with the right array. So that in turn will consider 1 and 3 as a separate list, and again it will have 2 arrays, left and the right, and the left will go from 0 to the first half of the array, which is, this will be the left array, and the right will go from the mid to the end. So this will be the right. This will be in the right array. So then here the length becomes 1. The length of the left array becomes 1, so it will exit out of this node to hit the base case. And now once the split is being done, the next step is to merge. So for the merge, we are taking the left and the right array and the result array. So here, for that, we have 2 pointers, I1, I2. One is for the left array, the second one is for the right array. And you keep checking both the arrays at a time and see which element is the smallest in both the arrays. The smallest element, you're adding that to the result and incrementing the index count of that array so that you can compare it next time. You can compare the next element next time. Let's see that how it is being done. So here, let's take this step, which will be easier to understand. So we have I1. This is A, and this is B, array A, and this is B. You can also say it as left and right. For now, I'm just saying A and B. So we have I1 for A and I2 for B. And here you have the result array. Now, I1 is initialized to 0 initially, and I2 is also initialized to 0. So now you're comparing the element at index 0 in both A and B. So I2 is also 0. So now you have 7 and 6. 6 is smaller than 7. So in the result array, we place the smallest element. Once you place the smallest element, you increment the counter of I2 because you don't want to check this element again. So we already placed the element 6. So we increment the counter from 0 to 1. But this will, I1's value will still remain 0. The next time we'll compare A of 0, which is 7, and B of 1, which is 34. So 7 is lesser than 34. So now 7 gets added to the result array. So once we add it, we increment the count of I1 from 0 to 1. Next time we have to check I1 at A at index 1. So now we have A at I1 at index 1. Now 57 is compared with 34. 34 is smaller, so you place 34 here to the result array and increment this counter. So I2 will be from 1 to 2. I1 will still remain 57. The next iteration, we check 57 is 57 or 35, whichever is lesser. We add that. So now 35 is added to the result array, and the count is incremented from 2 to 3. Now you compare 76 with, sorry, I think it's still 1. So we compare 57 with 58. So 57 is smaller, we add 57. Now you increment the count and then check 76 and 58. 58 is smaller, so you place 58 here. Now you have to increment the count from 3 to 4 after you place. Let's say we incremented the count to 4, but there are no elements after this. In that case, what we will do, we'll simply add the elements from this array into our result array, because there are no more elements to compare in this to compare against it. So what we are doing is just simply add those remaining elements to the result array, 76 and 86. So that's the condition that we have here in this merge step, where you have to index the left and the right, which will be initialized to 0. Have a for loop to go over the length of the sum of the length of both the arrays, the left and the right, for the entire length, like for the length of whatever the count of this length of A and B is. And we have the condition here to add it to the left, or to add from the left array or to the right array. So the condition to add to the from the left array is, first condition should be obviously left of I1 is less than the element in the right. But we also need to make sure that it's within the the count is less than the length of the array. Otherwise, we'll hit the end of the array and there'll be no elements to check against. In that case, so that's why we have this condition to check if I is less than the length of the array and that element is less than the right element. Or there are two possible conditions. So in this case, we can add it from the left array, or if we ran out of the right array. Ran out in the sense you have the index. Let's say we hit this position where we came to 3 and then to 4, there are no elements to compare. So in that case, we are simply adding the elements from the left array to the result array. So that's what this condition is for. Otherwise, you add it from the right array. And every time you add, you increment the pointer to compare the next element. That's about merge sort. So the complexity for merge sort is n into logarithmic of n, because you have two steps that we are performing here. The split is actually logarithmic of n, log n, because you're just splitting the array into two halves. You're not visiting the elements in an order. Like you split. It's similar to a binary search how we are doing. You're just splitting, adding the elements into left and the right. The merge step is what is actually you're visiting the element, every element in an array. So you have to visit every element in the left and right array, compare it, and then move it to our result array. So that takes n, and that's why it's n log n. Yeah, that's about merge sort. And next would be like another sort. It's called the quick sort, and that's most commonly used sort. So Here, quick sort is also similar. So let's see how. Here we pick a pivot element in the from the whole list, and what we're doing is simply arranging all the elements that are lesser than the pivot to the left of the pivot, and all the elements that are greater than the pivot to the right of the right portion of the array, and recursively do that. Find a pivot and arrange the elements that are lesser than the pivot to the left, the elements that are greater than the pivot to the right. So recursively, we keep doing that until it hits the base case of 0 or 1. And the complexity is O of n log n, and in the worst case, it would be O of n square. Let's go in detail of how this quick sort works. So here we have this entire array. The first step we are doing is to pick a pivot. Here 49 is picked as a pivot here. And what the first step we are doing is all the elements in the array that are lesser than 49, we are bringing to the left side of the array. And all the elements that are greater is being moved to the right of the array. Now left is being treated separately and right is being treated separately as a single array. And we keep repeating the step of finding the pivot, moving the elements in left or right. So first time when we are adding the elements to the left or to the right, the order maybe it doesn't have to be sorted exactly. So let's take this example here. 47, it's added in the same order that's in the original array. Like 47 was in the first position before 10. So we are adding as 47 and 10. We're not worried about if it's sorted or not in this step. So all we are doing is pick a pivot element, find the elements, find if the elements are lesser, then add it in the left half and then right half, and then keep doing that for the left and right. Okay, so there are two ways to do it. Now, when you are when you're moving these elements to the left and right, there are two ways to do it. One is like to have another array in it, to declare a new array and add the elements add the elements that are smaller than the pivot to that array, and have another array to hold the elements that are greater than the array. There is another way to do it, which is in place. So you can do the sorting in place. So in that case, we would be saving some space because every time you have to create a new array to hold the left and right values. But if you use this in place sorting, it saves us some space memory. So today, let's discuss about how to do that in place. So what we're doing here is you pick a pivot element, and then you have two pointers, the left and the right. So the first time, right will start at the end of the array, okay? And then we are moving from the right. You check elements until you find the element that is greater than the pivot. So once you find that element, we also move from the left, from the beginning of the array to find the element that has to be prior to this pivot element, that is smaller than the pivot element. Here, let's take this example. We have 56, 25, 37, 58, 95, and 19. So here we are choosing the pivot as 56, and we are traversing from the right of the array to see if there are if you find an element that that has to be to the left of the array, that is smaller than the pivot. So 30 is already smaller. So now we traverse the list from the left side from the beginning until we find the element that is greater to the pivot. So now that should be after the pivot. So now when we traverse, we find that 57 is bigger than 58 is bigger than our pivot element. So now once you have this, we swap these two elements. So 30 is swapped with 58. So the array becomes 56, 25, 37, and this is swap 30 and 58. Now again, we keep checking from the right towards the left until you find a value that should be to the left of the pivot, or it hits the left marker. Here, the left marker is here. So here, when you check, 19 is smaller than 56. Okay. Yeah, so when we are traversing from the left, we have to find the smaller element than the pivot. So 19 is smaller than the pivot. And when we are traversing from this direction, you have to find the element that is greater than the pivot. So here we have 95 that is greater than the pivot. Now 95 and 90, now we swap these two elements. Now again, we have to traverse until we hit the left marker, or if we find an element that's greater than the pivot. So here we have already hit the left marker here. We already hit the left marker here. So that's time to stop. So once we hit the left marker, so yeah, this step is already been done. Like 19 and 95, we swap it. After the swap, we are again trying to traverse to find the element that's greater than the pivot. Here it has hit the left marker when we keep traversing. So that's when we stop. And once we do that, we compare that with the pivot here. So 19 is smaller than the pivot. So finally, we are swapping that pivot element with our left marker, the index that we had here. Now, if you look at it, 56 is in the correct position. So this position, you don't need to move it again. 56 is already at the right position. So now what we have to do is do that similar thing that we did for the left array and for the right half. So we call quick sort from index 0 to 3. Then we call quick sort from index 5 to 7. Once we do that, we'll end up with the sorted. So here is the code for quick sort. We have a helper function that kind of takes the start and the finish, and the partition function that will give the boundary in a previous case, like how we found 56. So we'll give that boundary, which is 4. And then you recursively call this quick sort helper from 0 to your boundary, and then from boundary to the end. So that's this function, and this is a partition function that we discussed in the previous slides, where you pick the pivot element and then keep going from the left and keep coming from the right, and to find a value that's greater than pivot, and from left, keep coming from the left. And then once you find that index, we perform the swap. Once that swap is being done, then we move that, we swap the the first element, our pivot element, with that index. And yeah, it's the complexity is O of n squared, because you have to check, like here we have we have to check every element, like we have to keep checking that left and right for every pivot element. So the next one is the Radix Sort. We're not going to go in detail of this Radix Sort. We'll just have an overview of what the Radix Sort is. So Radix Sort is an non-comparative sorting algorithm. So how that's been done is the elements are sorted based on their like every position. Let's say we have this this array, these elements. So we are sorting the elements first in their least significant digit, the unit place. So we are comparing the elements, the unit place of each element, and they're sorting based on that. And Once that is done, we are moving to the 10th place and sorting the elements in that place, sorting the elements based on the values that are in the 10th place, and then keep repeating that until we find the most significant place, like until we complete the sort with the most significant digit. So here we have like the range is 3, so maximum we'll just go 3 times. First time is sorting based on the unit place, second time is sorting based on the 10th place, and third time based on the 100th place. So here we have 250, 02, 23. So from this array, just if you look at this, it's sorted in its unit place. So 0, 2, 3, 4, 5, 6, 7, 7, 8, and 9. Another thing is Radix sort is stable sort. What that means is the order of elements is maintained. So here 7 and 7, both of them are like has the equal value, but then here it's placed in the same order that it was in its original array. So 407 and 7. So that's why it's a stable sort. And then once you have that, once you sort based on the unit place, then you move to the 10th place, and now we see which element is smaller. So if there's only one digit, then you add leading zeros to that to compare it. So here 2 comes first, and then 407 comes second, and then 07 comes third. The reason why 407 comes first and 07 is because I explained earlier. It's because the Radix sort is a stable sort, and we maintain the order. It maintains the order that was in the original list. And now 9, 2, 3, 5, 6, 6, 8. So once that is done, we move on, sorting it based on the next significant digit, which is the 100th position. And that now we are adding leading zeros to compare. So 0, 0, 0, 0, 0, 0, all the elements in single digit, and then comes here, and then comes 250 and 407. So now we have repeated this until the number of for the range of the element, which is 3 here, and we have repeated it thrice, like to find it. And the time complexity is O of n into k, where n is the number of elements in the array, and k is the range of the elements. Here range is 3, so it's O of n into k. So that's about the Radix sort. Here it's in a tabular format, so you can make easy reference or for reference if you want to compare. So the worst case insertion sort, selection sort is O of n square, merge sort is n log n, and quick sort is O of n square. And in the best case, insertion sort is O of n, selection sort is O of n square, merge sort is n log n. I think you can read it or take a screenshot if you need. So that's about this. One thing to consider is like to have space, like whether you want an efficient algorithm that based on space. So in that case, you want to choose, decide like which algorithm to use. For example, merge sort, it might take more space. So what is the trade-off that you have, space versus the other complexity, so time complexity? That's something that we want to consider. Yeah, I think we discussed that. And other sorts that could be helpful is heap sort. We haven't discussed that today, but shell sort or other sorts that you want to take a look at it if you're interested in it. Yeah, I think that's about it. We've come to the end of the presentation. Any questions, thoughts, comments? If you want me to go over anything again, I'd be happy to do so.